Hello everyone. Today we'll be talking about design of hollow block slabs. The concept of hollow block slabs that in case of large span, the thickness of the slab has to increase if you are using a flat slab. So if you are having a flat slab that's really significantly thick, you are losing a lot because the own weight is heavy. You will have to design something very thick. You will pay a lot for the concrete and you will pay a lot for the steel. So now the better thing is to create a light chunk of volume within your concrete, whether using hollow blocks made out of concrete or foam. Even foam is even better because it's significantly lighter. So these are sample weights of material used in hollow block floors in kilonewton per meter square. So if you look at foam, if I'm talking about a two-way hollow block slab, it's 1.2 kilonewton per meter square. Of course, I mean, compared to cement or concrete blocks, it's significantly less than concrete blocks. So this thing could be placed in a one-way orientation like this, or in a two-way orientation. The one-way orientation, you have what is called the ribs. The ribs are the concrete mass in between the row of blocks. So here you have the blocks, then you have ribs in between them. So actually the ribs are the ones that carry the steel, in which the steel is placed. So here the steel is placed in the ribs, okay, and you don't depend on the blocks to carry any weight. Actually the blocks are carried, you are not carrying anything, okay. So the difference between the one way and the two way is that the one way, the ribs are oriented in one way. However, the two-way, you have two-dimensional orientation of ribs. When dimensioning one-way hollow block slabs, you first need to understand the concept that the beams could be either projected or hidden, or you could have some projected and some hidden. So if you have projected beams existing, the solid part of the width shall range between 0.2 to 0.5 meters. If the beams are hidden, the solid part of the width should range between 0.8 to 2 meters. So these are the hidden beams. Of course, architects prefer hidden beams because they don't like anything projected for aesthetic and other purpose and usage and all that stuff. So the number of blocks per direction depends on the dimension of the blocks and the number of cross ribs. So here, if you look here, so here you have 500 times n2. What's 500 times n2? Because here, this is the 500. This is the dimension of this dimension times n2 minus 100. Okay? We'll discuss in details how is this calculated. So the issue of having cross ribs, it depends on the dimensions and it depends on the load, as we discussed. So the code provisions tell us that the clear spacing E should not exceed 700 millimeter. Actually, this E is the dimension of the blocks. Okay. B should not not be less than 100 millimeter or T over 3. The upper reinforcement above even the blocks should be a minimum of 5.56 per meter. The thickness of the slab above the blocks should not be less than 50 millimeter or E over 10 as shown here. Whether you have cross ribs or not is governed by the load, the live load, and the span. So if you have a small span less than 5 meter and live load less than 3 kilonewton per meter square, you don't need a cross rib. If the span exceeds 5 meter or the load exceeds 3 kilonewton per meter square, the live load exceeds 3 kilonewton per meter square, you need one cross rib. If both exceed, if the span exceeds 7 meters and the live load exceeds 3 kilonewton per meter square, you need 3 cross ribs. So let's look at the design of the ribs. First, you calculate the load. W ultimate is 1.4 flooring plus the blocks per meter square plus 1.6 W live load. Then the effective width is B capital, which is E plus B small. The ultimate load per rib is actually, so now what we calculated up was the pressure. So now we need to multiply this pressure by the width to get the load per rib. So this is B times W ultimate. Then the section with the maximum positive moment is designed as a T section. The section with the maximum negative moment is designed as a rectangular section. This is how the blocks are oriented, and this is how the blocks are distributed, and this is how the ribs are reinforced. So you reinforce you place an reinforcement, you state it per rib, not per meter like flat slabs and regular slabs. For hidden beams, the depth is small, however they are wide, so they are heavily reinforced. Sometimes you need to increase the depth by 50 millimeters, so you take part of the flooring through within the depth. The concrete shear strength for hidden beams is 0.16 root FCU over gamma C. Of course, and the Q ultimate is Q ultimate over BD. The minimum shear reinforcement is BS times 0.4 F over F yield times Q ultimate over QC. Let's take a nice example here. Here you have a floor that weighs 2 kilo, with a flooring weighing 2 kN per meter square, live load of 4 kN per meter square. FCU is 40 megapascal, F yield is 400 megapascal, and you have this plan. First, we'll dimension the thing. You choose 400 by 200 by 200 cement blocks. Therefore, E is actually equal to 400 millimeter, which is less than 700, so it's okay. TS is the smaller of 50 millimeter and 40 over 10, so let's take it as 50. So the total T is TS plus T blocks, so now it's 250 millimeter. B is the bigger of 100 millimeter and 250 over 3, so B is equal to 100 millimeter. So the capital B is E plus the small b, so this is 500 millimeter. If you go to the load calculations, from the table, the own weight of the cement blocks is 3.3 kilonewton per meter square. So W ultimate is 1.4 times 2 plus 3.3 times 1.6 times 4. This is 13.82 kilonewton per meter square. I want you guys to think of comparing this to what we got from a flat slab before. If you remember, we got from a flat slab before something about 18 kilonewton per meter square. Here it's 13.8. So there is more than 4 kilonewton per meter square of savings in the ultimate load. So this will make a big difference in our design in terms of the amount of reinforcement you will be using within this slab. So W ultimate rib is this number multiplied by B. So this is 6.91 kilonewton per meter. First, you need to have the block arrangement done. So as the live load is more than 3 kilonewton per meter square and the span is less than 7 meters, only one cross rib is needed. The width of this cross rib is 100 millimeters. So simply, in order to do the exterior bay, you start with the exterior bay. You will assume the dimension C1 to be 300 millimeter and the dimension C2 to be 600 millimeter. So the clear span is 5400 minus 300 plus 600. This is 4500 millimeter. The number of blocks will be 4500 minus 100 over 200. This is a clear 22. Let us say that you made another assumption. Maybe you did an assumption of C1 is equal to 400 and C2 is equal to 800. In such a case, you will get a number which is a fraction. So if you get a number that's a fraction, you need to either round it up or round it down and recalculate the values of C1 and C2. Then you need to recalculate the values of C1 and C2. The interior bay, you'll assume C3 is 650. So the clear span is 5400 minus 2 times 650. So this is 4100. 4100 minus 100, which is this is the value of the cross rib. So this over 200, this is 20. So this is the 20 this 20 is a whole number. Again, maybe if I assume this as a 600, I would have got a fraction here, a number with a fraction here. So I should have rounded it up or down in order to get a number that is a whole number in terms of number of blocks. Therefore, get a value of a whole number for C3. The block arrangement in the y direction is very similar. So similarly, you will assume the C4, which is 300. So now the clear span is 6200 minus 2 times 300, which is equal to 5600 millimeters. If N3 is the number of blocks, then the number of ribs is N3 minus 1, such that 400 N3 plus 100 times N3 minus 1 is equal to 5600. Therefore, N3 will be 11.4. Therefore, we'll let it to be 11 and recalculate C4 from the relation 6200 minus 2 C4. This is 11 times 400 plus 10 times 100. Why is 10 times 100? Because this is the number of ribs. We have 10 ribs here, and 11 times 400 because we have 11 rows of blocks here. Therefore, the C4 will be 400 millimeters. So this is what I was talking about, that you will round it down, or actually not round it down, you will truncate any fraction you will get in terms of n. So if you got here, for example, it was a 22.5, you should truncate the 0.5 and get a 22. If here it was 20.5, you'll get it 20, and then recalculate the values for C1, C2, C3, C4, or whatever C you are calculating. Then you will design the ribs. The section is designed as a T section. M ultimate is the W ultimate B times L squared over 10. D is 250 minus 30. So this is, and B capital is 500 millimeter. If we use the C1J charts, you will get that AS is equal to 277 millimeter square. So you will use 2514 millimeter per rib. Similarly, we will design section 3. From the other side, section 2 is designed as a rectangular section. So you'll calculate the moment. It's 20.15 kilonewton meter. D is 220 millimeter. R1 is using the R1 omega relations. Again, you will find it is AS is 2 phi 14 millimeter per rib. Designing the hidden beam is like any beam. So simply it's receiving the loads from the sides. So you'll multiply the clear span times W alternate plus the load on the beam. Then you will calculate the positive moment, which is WI squared over 11. Then you'll find you need 11 phi 20 millimeters in the positive side. On the negative side, you needed 14 phi 20. The edge above the support you will need, because the moment is WI squared over 24, it will be 6 phi 20. Of course, it needs to be specially considered for shear, so you will calculate the shear force at D over 2 from the face of the column. Then, so you will find it to be 270 kilonewton. The ultimate load is the ultimate shear is 0.8 megapascal. QCU ultimate is 0.83, so we only need the minimum stirrups, which are equal to 405 millimeters square. So we'll get 6 branches in order to be able to fix our bars. So 6 branches of 5 phi 10 per meter run, as shown here. And it's very important to understand that we have this detailing in this manner in order to be able to fix our 6 bars here, the stirrup hangers. And this is the detailing of the hidden beam. This is the detailing of the rib reinforcement. But what about two-way hollow blocks? Two-way hollow blocks are very nice in terms of throwing the loads in 2 ways, in 2 dimensions. Very similar to what was done in two-way slabs. We have the very similar concept, that you have one dimension over the other, is the ratio between them is less than 2. So simply you will place reinforcement in both directions, and again you will have this M's MA or MB, which is 1.87.76, very similar to what we had in the regular slabs. And after multiplying this M by B and this M by A, divide this over that, you get an R. But take care, this R and the alpha and the beta are not the same alpha and beta for regular slabs, regular solid slabs. They are different here. But the same concept applies here, that MA is equal to W alpha A squared over 8, MB is W beta B squared over 8. The same concept, but the difference is in the numbers themselves. So if we redesign example 1 using two-way hollow block system, the dimensions are the same. Okay, so the same dimensions didn't change, the same cross section didn't change, the same B didn't change, but the load will change, because from the table the own weight of the two-way hollow blocks is a little bit different, because it's surrounded by concrete, so it's a little bit heavier. It's 3.8 kN per meter square. W ultimate will be 14.5. So from R is 6.2 over 5.4, 1.15. So alpha is 0.507, beta is 0.299. So now this will be redistributed with a really good ratio. I mean, this is nearly half of the thing. So here, when you calculate the ultimate load on the rib in one direction, it's only 3.68 kN per meter. Compare this to the other number we got from the previous example. This is a real big saving here. Same thing in the beta direction, the second direction, and when you multiply beta by W ultimate, you get 2.17. So the block arrangement is very similar. You'll assume C is 500 millimeter. The clear span is 5400 minus 2 times 500. This is 4400. 4400 minus 400 over 500. This will give us an 8 ribs in the x direction. Very similar thing in the y direction. If you assume C2 as 400 millimeters, 6200 minus 2 times 400, this is 5400. 5400 minus the 400, which is the C2 over 500, this will give us 10 ribs in the y direction. Very similar to what we have done before, we'll calculate M ultimate in X. But now we'll find it lighter. I mean, if you go, when we design it, the AS is only 147. You only need 2510 millimeter per rib. Compare this to the 2514 in the one-way direction. This is cost saving. Similarly, the rectangular section number 2, if you look at it, you will have a very similar issue, that again you got 2510 millimeter per rib. Okay, but now I'm using the R1 omega because I don't need the C1J. You could use the C1J if you want. Design of ribs in the Y direction, since actually here we used in the X direction, we only needed 2510 millimeter per rib. In the Y direction, for sure, we will not need anything more than that, because this is the absolute minimum that you could place. So you will also place 2510 millimeter per rib. And as you could see, this is significantly cost saving. What about the projected beams? Projected beams are regularly like any beams. So projected beams are beams like any beams. You shouldn't worry about them.